Hello, everyone. Mr. Sutherland here. Getting ready to start our final chapter of the year. And I just want to again say how proud I am of you guys for doing the work of sequences and series on your own. E-learning's not easy. You don't get to ask those questions in the moment. We don't get to practice and get that feedback. But I'm very proud of the work that you guys have put into this so far. Our last unit is the foundation of calculus. And so if you're a junior and you're taking calculus or not, it could be AP or non-AP calc. This is a huge idea. It will give you a good start for next year. If you're a senior and you're going to take calc at the college level, this again for you will be a great foundation. This is what we're covering here is usually in the first week or two of calculus. So the idea is to give you guys a little head start, a little background knowledge, not expecting you to master it this year, so that when you see it next year, it can be a little more familiar to you. So we're going to talk about the idea of a limit. And we're going to start by looking at limits from graphs, which we've kind of done this year, and I'll go back to that here in a moment. Looking at tables, how to evaluate limits algebraically, and then something called the average rate of change and difference quotient, and then the big idea of calc. First semester Calc 1 is the idea of the derivative, and we're going to talk about what that is. So you can see in here we'll have some review built in, we'll have some quizzes, so you can see we have 5 really lessons left this year. So we talk about limits. Let me go back up here on the side to where we first saw limits this year. We've done a bit with it. This is from our first notes on graphing rational functions, and you can see we evaluated some limits. We did limits as x approaches infinity in behavior limits, and we did limits as you're approaching asymptotes. So it's the same idea, except this time we're going to look at limits as you approach a point, as well as these asymptotes. So the note sheet that you can print out or just take these notes in your notebook. You're going to be referring to a lot of graphs when you're doing these problems, obviously. Let's first of all just quickly remind you the notation of a limit and what it means. So if we see this notation, and it is LIM x with a little arrow a of f of x equals L. And what this statement means is as x approaches a, so as my x values get closer and closer, whatever that number is, the y values of the function approach L. So L is a y value. Now, it could reach that y value, it could be defined there, it could not be there, and we'll see some different interpretations of that in a moment. And then the other important aspect from that previous note sheet to remember is that when you see the limit as x approaches a with a little negative sign as a superscript, that means you are checking the graph from the left. That's what's called a left-hand limit. So the little negative sign is going to be from the left. And if you see the limit x approaches a with a little positive sign as a superscript, that means you're looking at the right side and approaching it from the right. So the little plus sign is going to mean from the right. Now, maybe you've heard sometimes where they say the limit doesn't exist. What does it mean for a limit to not exist? Well, let me give you a quick example. And here's what you need to know. The limit as x approaches a, f of x equals L. So it equals a value. There is an answer. If and only if the left-hand limit, so as x approaches a from the left, is equal to the right-hand limit. So if those limits match, then the limit exists and it is that value. So an example of one that does exist would be, let's say this is my a value here. And let's say I have a graph that looks like this. Let's say it's undefined there. and goes down, I would say that this limit exists because as I approach A from the left and as I approach A from the right, I'm headed towards the exact same value. They're going to meet. It doesn't matter that the function's not defined here. In fact, this point could be down here. That actually has nothing to do with the limit. The limit is what are most of the points on the graph doing? As you approach the left and you approach the right, they're heading towards the same value. So this would be an example that does exist. Now, let's show a quick example of a limit that does not exist. So let's say we have our A value right here. And let's say, I'll do it in a different color here. I have a function that looks like this. So we can see for this function, as I approach A from the left, and as I approach A from the right, I'm headed towards different Y values, whatever these are. Maybe this is 1 and this is 3. Those Y values do not match. Therefore, we would say this limit does not exist, and you can just write D and EAT. So let's take a look at some very basic examples here at the bottom. So using the graph, answer the following questions. So in A, I want to know what's f of 2, what are the limits, and then is it continuous? We're going to try to make a connection between continuity and the point here. So the first question is, what is f of 2? So f of 2, well, that's just a horizontal line that goes through 3. So f of 2 is 3. The limit is x approaches 2 from the left. Well, that's this. I'm approaching 2 from the left. Well, that's 3. Even though I'm already there, we say approaching 3, it can equal that value. As I approach 3 from the right, or 2 from the right, I'm also getting close. I'm going towards 3. I am at 3. It doesn't matter that you're at that value. And then since those two answers match, we say the limit as x approaches 2 is 3. And this obviously is a continuous function. And notice, to be continuous, we'll see if this holds, this limit and this point are the same. Now let's look at this second one here. So I have a graph that's undefined at 2, and but there is a point up here. So if I asked you what is f of 2, f of 2 would be 4. Now if I try to evaluate the limit, as I approach 2 from the left, I'm approaching the y value. It's getting closer and closer to -1. As I approach 2 from the right, again, I'm getting closer and closer to -1. Since those match, we can say the limit exists and it is equal to -1. But this is not a continuous function, right? I can't draw this without lifting my pencil and doing this other point or jumping to the other branch. And notice, f of 2 does not equal that limit. That's going to be a key to this whole definition of continuity. All right, final question. F of 2 on this graph. Well, f of 2 is defined here. It's sort of that filled in, so that's 1. Now my limits. So as I approach 2 from the left, I'm getting closer and closer to -2. And then as I approach 2 from the right, I'm getting closer and closer to 1. Those do not match. When those do not match, the limit does not exist. And obviously, this is not a continuous function. So to be continuous, the limit has to exist, and then that limit has to match the point, has to like fill in that hole. Like you can have a hole like this one does to be continuous. So what I'd like you to do now is on the back, there are a couple graphs where I ask several questions about limits, evaluating the functions. And what I'd like you to do is try number 2, pause the video, try it, and then unpause it and see how you do. And then I'll go through this one. Okay, let's take a look at number 2. So the first question asks, what's the limit as x approaches -2? So I'm going to look at x equals -2. Here's the point. As I approach from the left and as I approach from the right, I'm headed towards the same y value, and that y value is 1. So the limit as x approaches -2 is 1. Now, the limit as x approaches 3. So I'm going to go to my graph. There's x equals 3 as I come from the left and as I go from the right. Both of those arrows are headed towards the same exact y value, and that y value is 0. So this limit is 0. But f of 3, if we look at that point, is actually right up here, which is 1. So we know, obviously, it's not continuous there. Now, the next one, x approaches 2 from the left. So I'm going to look at x approaches 2 from the left. The y value I'm getting closer to is 7. X approaches 2 from the right, so I'm going to go over this area here, 2 to the right. I'm getting closer to 1, which that means the limit as x approaches 2 does not exist. And that's it with limits graphically. We've done asymptotes this year. We haven't really looked at limits around holes or limit at points where it's continuous, but you just follow what the graph is doing. All right, same thing. Look at number 3, pause the video, try these 6 problems, and then we'll go over it here in just a moment. All right, let's take a look at these. So the first one, x approaches -8. So I go to -8 from the left and from the right. I'm approaching the same y value, and that y value is 1. X approaches 6 for the next one. So I go to 6 from the left and from the right. I'm approaching the same y value, and that y value is 5. F of 3. Now notice f of 3, there's a hole there, and there's no point anywhere. So I just wanted to talk about the word you would use here. This, we would say f of 3 is undefined. Not does not exist, but instead here we would use undefined because there's nothing there. All right, last one. X approaches -3 from the left. So here's -3. As I go from the left, my graph is heading up, and it says there's a vertical asymptote here at -3, and we could sketch that in. And so this limit is headed towards infinity. The limit as x approaches 3 from the right is also headed to infinity. Now here's the thing. Infinity doesn't necessarily equal infinity. Right? It doesn't represent a finite definite number. So we actually say this limit as x approaches -3 does not exist. And that's a tricky one, but one you'll get used to seeing as you explore limits a little more. So I hope this has given you a good foundation, a little review of what we've done with limits graphically so far this year. And I will see you again soon. Talk to you soon. Take care.